When data travels through a copper wire, it moves incredibly fast. But eventually, that electrical signal hits a physical barrier, like a fiber optic cable transition. At this lowest level, OSI Layer 1, the physical layer, is strictly bound to its medium. It only knows how to move raw bits as voltage, light, or radio waves. It does not understand destinations. Moving up to OSI Layer 2 introduces MAC addresses, allowing devices to exchange data frames. But this data link layer is entirely local. It can only route traffic within a single network segment. To cross these physical and logical boundaries, to move data from a local switch in Tokyo to a server in London, we need a bridge. That bridge is OSI Layer 3, the network layer. The primary engine driving this layer is the Internet Protocol, or IP. To achieve global connectivity, IP relies on a specific sequence of mechanics: addressing, encapsulation, and routing. But to make this system scale across billions of devices, its architects made a counterintuitive choice. They intentionally designed IP to be entirely unreliable. This lack of a delivery guarantee allows a single protocol to span the entire globe without the processing weight of a continuous connection. Without this Layer 3 logic, every network would remain an isolated island of hardware. Passing data securely and accurately across network boundaries requires a strict 4-step operational pipeline. This diagram illustrates the sequence. Step 1 is addressing. Every network device must be assigned a unique Layer 3 IP address as an identifier. Step 2 is encapsulation. To transit the network, the transport layer data payload must be wrapped for delivery. Here, the router takes the entire transport layer payload, the segment header and data, and wraps it inside a new IP header. This forms the IP packet. Notice the green data block remains untouched. The router does not examine or modify the application data during encapsulation. Returning to the pipeline, step 3 is routing. The packet is directed hop by hop across the network. Step 4 is de-encapsulation. The destination device receives the packet, verifies the IP address, and strips away the IP header, passing the payload up to the transport layer. Because the IP header is the only part examined by Layer 3 devices, the transport layer segments can be packaged by IPv4, IPv6, or any future protocol without requiring any changes to the application data itself. For IP to function efficiently at a global scale, it was built on a specific design philosophy, operating with the lowest possible computational overhead. This graphic highlights the first major characteristic: IP is connectionless. The sender drops a packet onto the network without establishing a dedicated circuit. It works exactly like dropping a letter into a mailbox. There's no preliminary handshake to confirm the receiver is ready. Best effort means IP provides zero guarantees of delivery. It does not track lost packets, it doesn't reassemble out-of-order data, or retransmit corrupted files. It is inherently unreliable by its design. The third characteristic is media independence, displaying 3 distinct physical transport methods. Because the IP packet is self-contained, the exact same packet travels as electrical voltage over copper, light pulses over fiber optics, or radio waves through the air. The internal data never changes. By offloading complex error correction and delivery tracking to upper-layer protocols like TCP, IP trims the fat. It trades guaranteed reliability for massive frictionless speed. We can see this low-overhead design physically manifested in the layout of the IPv4 packet header, shown here. The header is a compact 20-byte block of metadata. A router reads it row by row, 32 bits at a time, strictly left to right and top to bottom. Here, the time-to-live field acts as a safeguard, dropping by 1 at every hop to prevent infinite routing loops. Next, the protocol field identifies the payload's next-level service. Finally, the source and destination IP addresses dictate origin and endpoint, remaining unchanged during transit. These specific binary fields contain everything a router needs, allowing hardware to make instantaneous, independent forwarding decisions, moving data efficiently without connection overhead. Despite its efficiency, the IPv4 header contains a fatal architectural limitation. Its address space is restricted to exactly 32 bits. Mathematically, 32 bits generate a maximum of roughly 4.3 billion unique IP addresses. As the internet exploded, that hard cap led to severe address depletion. We simply ran out of numbers. To keep the internet functioning, engineers deployed a stopgap measure called Network Address Translation, or NAT. NAT allows multiple internal devices to hide behind and share a single public IP address. However, NAT forces routers to modify headers in transit, adding processing latency, and breaks true end-to-end connectivity by masking the actual internal hosts from the wider network. The permanent architectural solution is IPv6. As this graphic illustrates, it expands the address format to 128 bits, generating an address pool of 340 undecillion. That is enough unique identifiers to assign a public IP to roughly every grain of sand on Earth. Along with the increased address density, IPv6 eliminates the functional requirement for NAT. It also streamlines the packet header, reducing the fields a router checks during processing. The transition to IPv6 removes processing overhead and restores the direct host-to-host connectivity defined in the original OSI Layer 3 model.